Thanks for tuning into this revision zone video. In this video, we'll be looking at Hess cycles and Hess's law with some applications using enthalpy changes of formation and combustion briefly. If you're unsure about those definitions, please go and see our part 4 video within this section to help you with your understanding on that. So we're going to look at Hess's law first. What exactly does it state and what does it mean? And we'll try and apply it to some basic examples to begin with, generic examples, and then we'll lead on to enthalpy of formation examples and combustion examples too. We won't go through the calculation in this video. That will follow in latter videos. So let's get stuck in. What is Hess's law? This states that the enthalpy change of any reaction is independent. It's quite important, independent, sorry about that line, not very clear, but is independent of the route taken. It's a bit better. So that essentially means, and this is what we're going to look at next, what does it essentially mean? It means that we can work out the enthalpy change of any given reaction, even if it is impossible to measure it directly from experiment and using Q equals mc delta T, which we will have covered in previous videos. So again, if you're unsure of that, please go and see our previous videos. So we're going to start off with this example here. Just very generic, like I said in the introduction, we're going to start with these. What it means is if I want to get from point A to point B, normally the easiest way is to go in a straight line. Now, that means what I'm trying to depict here is if we're trying to find the enthalpy change for a particular reaction, let's call this delta H R. Let's put the standard state and condition symbol in there. That means that I would want to react my A, get my B, measure my temperature change, okay, and work out the energy transferred, use my limiting factor to work out the enthalpy. But what if I put something in the way, an obstruction that would not allow me to, let's say, measure the temperature change? Maybe it's too dangerous to get from A to B, and therefore it's not worth actually doing this experiment directly. Another way of looking at it is, well, if I want to get from point A to point B, but I put a wall in the way, so you could not get through from A to B, well, the alternative is to go via a different route. And what Hess's law states is that the energy required to get from A to B would be exactly the amount of energy required to go via this route. And this is what we're going to look at here. So what I'm trying to illustrate in this little diagram is, I'll draw it a bit more clearly here, is let's say I couldn't get from A to B, but I could get from A to C quite safely, or I could measure the temperature change for that reaction. And I could also go from C to B. And what I'm going to do for simplicity is we're going to label these enthalpy changes as delta H1 and delta H2. That means that if I can measure this enthalpy from A to C, delta H1, I can use that enthalpy, add it to delta H2, so from C to B, and that will be equal to delta HR. So another way of writing that is that delta HR is actually equal to delta H1 plus delta H2. And I'll just put the standard state symbols and I'll add them over here too. Okay, for consistency. So what I mean is if I want to start here, want to end up there, but I can't go via delta HR, I go this way with this arrow, and I go with this arrow as well. Okay, so it just means I'm going via an alternative pathway, if you like, an alternative route, an independent route, which is what I tried to underline earlier there. I could also look at it from a different example. Now, this is Hess's law. So what this diagram here is depicting, so this diagram here in blue, and a little bit of red, is a Hess's cycle. And the cycle represents this independent route taken. Now we're going to do an alternative approach as well. It doesn't necessarily just have to go through one additional stage like C, it can go through multiple changes. And Hess's cycle can be applied to many things, and that principle can be applied to calculate a lot of other enthalpy changes. And it doesn't have to be via just one other stage. We can go via many stages. So what I mean by that is that we don't have to necessarily just go through one stage C. We can go through multiple stages to work out this delta HR. That means that I could, let's say I do know the enthalpy change to get to get to C, and let's say that's delta H1 again, but it doesn't, I don't know C to B, but I can get from C to D, and then I know D to B. So I know all these individual enthalpy changes, and we'll call these delta H2 now, and delta H3. What I'm actually going to do here is to make this a little bit more realistic, is rather than using D to B, let's say we only know B to D. So we know the opposite direction. So how does this work out then? Well, let's have a look at what we've got to do. So we got to start at A and we want to finish at B. That means, but I can't go directly from A to B. I have to go to C, C to D, and D to B. Now what that means is that I know this enthalpy change, and this is going in the same direction as that arrow currently for delta H1. We're not going in the opposite direction. Think vectors. If you're a mathematician, think vectors. We're going with the same direction of this energetic value of delta H1. I'm also going, I'm going to go into, I'll go through delta H2 here. I'm also going in this direction. So that means I'm going with this one here. I'm not opposing this. But from D to B, I know B to D, that was the value as given, and that's going in the opposite direction. This time, I'm going against this arrow. So what does that mean for a description of delta HR in this case? Well, what that means is delta HR is equal to delta H1 plus, I'm adding this because it's going in the same direction, delta H2, but this time I am going against this arrow. This time I'm going against this arrow, so this delta H3 becomes minus. I'm going against that direction. It's a bit like vectors, like I said, you oppose it, so you put a minus in front, and that minus is quite important. So the sum of these three enthalpies will equate to delta HR. I'm going via an indirect route. And this indirect route will be equal to the enthalpy of reaction, which I've obviously put up here, but I'm just putting there as well. So I hope that makes sense. It might be worth just rewinding the video and going through that again. So let's try and apply these principles above to a very common example that you will have come across in chemistry, and that is the thermal decomposition of calcium carbonate. So if we start off by writing the actual decomposition, we'll not always write our state symbols in, and that forms calcium oxide, solid, plus carbon dioxide. And I want to make sure that it is balanced all the time. So that equation is actually balanced. You can spend some time and have a quick look at that. I'm going to call this energy change delta HR, like we have in the past. Now delta HR is just, like I said, enthalpy of reaction. We do have the previous video to this that discusses what delta HR means, so please go and revisit that. Now, why can't I measure this? Why can't I measure this directly? Okay, why can't I go on get the temperature change and use Q equals mc delta T? Well, this is a thermal decomposition reaction, and thermal decomposition means it is endothermic. That should mean that I should get a temperature change that is going down, it's decreasing. Now, hopefully you've done this at school and you've tried to decompose it. And the way we decompose it is we get a test tube, we fill it with calcium carbonate, we heat it. And you might have a delivery tube going from here, from the top of this test tube, into some lime water to detect the CO2. However, this is requiring heat. We know it's endothermic, and we know that the temperature should go down. Now, if I'm going to decompose this and I'm going to put a thermometer in there to measure that temperature change, I am not going to get a decrease in temperature. The change in temperature will not look as if it's decreasing. I need it to go down, but will it? No, it won't, because it is being heated by a blue Bunsen roaring flame on a Bunsen burner, and that's not going to allow me to measure an accurate temperature change, which means we have to use an alternative way to measure the enthalpy of this reaction. Now, I'm not looking at these calculations in this video. We're only looking at the setup and trying to make sense on the setup. The next video will be looking at the actual calculations, and we'll look at how we can actually calculate delta HR. But it is pretty much just plugging in values once you have this concept that we've looked at above. So what can I do? Well, what we do is we say, right, what other reactions can I do to calcium carbonate over here and calcium oxide, which will give me the same products? Okay, in this particular case, we use the reaction of these two bases with acid. If I react calcium carbonate with HCl, I will get calcium chloride, aqueous, plus CO2 gas, squeeze that in, and H2O liquid. Okay, those are the things that I'm going to get. Whereas if I get calcium carbonate, I'm going to get, and I'm going to just write that one underneath here. I'll do that in a different color just so it stands out. So calcium carbonate, calcium oxide. Did mean calcium oxide. So now if I do it with calcium oxide, that with HCl, aqueous, that will give me calcium chloride plus H2O liquid. We always need to make sure that these equations are balanced. So if I go to the top left first, I need 2 there, and that will balance out my elements there that I require. I need to do the same thing here, and I need 2 HCl to balance this equation too. And what I'm going to do is I'm going to call these delta H1, assuming they're done in standard states conditions, and delta H2. Now, there is a similarity here. Let's just have a quick look at something first, though. Just going to pick out a highlighter. If I look at calcium oxide there, I just shade over that, I see that calcium oxide is over here too. So if I look at this equation here, I can almost overlap that part of the equation on top. Okay, don't worry about this CO2 just yet. So that means that if I react calcium oxide and I try and construct a Hess cycle similar to this, this arrow is going from calcium oxide to calcium chloride and water. So what I'm going to do, I'm going to have the arrow going down. That's delta H2. I'm going to put my products here, calcium chloride, aqueous, plus H2O, Now, you're probably wondering, where does this HCl go? Well, the HCl we can quite simply put on the arrow. So I'm just going to write that in black, and we can put plus 2HCl on the arrow. Now, sometimes in text, you might not even see that. Sometimes they just leave that out. But for this reason, just so that you understand what's going on, we're going to incorporate that into the Hess cycles. I suggest you do, just helps you understand how these equations are used to build up this overall Hess cycle. And the next one I'm going to do in red. So we're going to now move over to the calcium carbonate reaction. Now, if we look at this, calcium chloride appears here in the equation and here within our semi-built Hess cycle. So that can overlap there. What we also have is we have some carbon dioxide, which I'll come back to, and water, which we already have water here. More importantly, a calcium carbonate solid that is here. So I can actually overlap this over. And this arrow is going from calcium carbonate to calcium chloride. So I have an arrow going down. Okay. And this is, like I said, delta H1 is reacting with 2HCl, the calcium carbonate. So I'm just going to write again in black, plus 2HCl, and then I'll put aqueous there as well. Right, there are a few things that we need to do. We need to make sure everything's balanced out. I'm missing a carbon dioxide here. So I need to really add that carbon dioxide at the bottom. Okay, because this red arrow here is an equation, it's part of an enthalpy change, which is from our delta H1 from this equation. It's got to balance on either side of this arrow. So it's one calcium, one carbon, and now I need that carbon in from the carbon dioxide, 3 oxygens, 1, 2, 3, and so 2 from the carbon dioxide. The HCl therefore needs to be unarrowed so we can account for the hydrogen, the extra hydrogen, and chlorine within the bottom part of this Hess cycle. So that is really important, that everything is balanced and everything works out as individual reactions and individual equations if you were to look at delta HR, delta H1, and delta H2. Now, CO2, just to bring it back a notch there, that CO2 will cancel out this CO2. If you're wondering, well, there's no CO2 here, well, yeah, you're absolutely right, there is no CO2 here. By putting this CO2, and that's why it's really important here, within the equation, it actually means that it cancels out this CO2 here, if we're looking at it from delta H2. Now, how do I work out delta HR when it comes to actually calculating using this Hess cycle? Well, what I normally say to my students is put a dot where you want to start, a dot where you want to end, and you are going to go from dot to dot via an indirect route. So you're going to go down, across, and up. Now this is going with this arrow, so this is a plus. This part here for the delta H2, the blue arrow, is going against the green arrow, so it's a minus. So how does that translate to what delta HR is equal to? So delta HR would be delta H1 minus delta H2. And that minus there, this minus here, is representative of the fact that we have to go in the opposite direction to delta H2. So it's really, really quite important. Now, this is quite a tough example. It's kind of been thrown in the deep end here, but it is a common one that can come up, and it doesn't involve either formation enthalpies or combustion enthalpies, but it illustrates the fact that Hess cycles can be used to determine enthalpy changes, which are difficult to determine directly via experiment, via other reactions that we can measure the temperature change of. So we can use a polystyrene cup calorimeter, put solid calcium carbonate, excess acid, work out the temperature change, and therefore use Q equals mc delta T for delta H1 and do the same thing for delta H2 and use those experimental values to calculate my enthalpy of reaction or the thermal decomposition enthalpy for this particular reaction. And it's a typical example that's used. Now we're going to have a look at the use of Hess cycles using the enthalpy of formation and combustion. Now, if you're not sure about those definitions, please go and have a look at our part 4 video, where we do look at the standard enthalpy definitions of formation and combustion. Now, formation and combustion enthalpy Hess cycles are very much used at the start of this topic when introducing Hess cycles and constructing them. I'm going to go and use formation first, and hopefully then that help us understand combustion. Now, just to recap the definition quickly, the enthalpy of formation is the amount of energy transferred when 1 mole of a substance is made from its constituent elements at standard states conditions. The enthalpy of combustion, on the other hand, is the energy released when 1 mole of a substance is completely reacted or burned with excess or enough oxygen to form complete combustion in standard states and conditions. Now, we're going to start off with the example of enthalpy of formation. We're going to use the same equation for each formation and combustion. So the one we're going to look at is hydrogenation of ethene, or reduction of ethene, I should say, not hydrogenation. It's better to say reduction. So that is ethene plus hydrogen gas gives us ethane. Now, again, I've kept state symbols in there just to make things very clear to the examiner that I know what these are in their standard states and conditions, and it's always good practice to do that. I'm going to call this delta H. Oh, I can label this anything. I can call this delta H1 if I wanted to, and then number the others accordingly, but I'm just going to keep it at delta HR. Now, with formation, what I'm looking at here is I'm looking at the enthalpy of formation of each of these individual substances. It is worth mentioning here that if you ever see an element on its own, the enthalpy of formation of any element, any constituent element, got that H there. Let's do that again, actually. Let's get rid of that. So the enthalpy of formation of any element, now I could put an F after here or in between, I'll put it after here, it doesn't really matter, of any element, as long as it's in its constituent state, it will always be equal to 0 kilojoules per mole. Because the definition states that it's the amount of energy to form 1 mole of a substance from its constituent elements. Remember, constituent elements means what do they exist at standard states conditions. If I take hydrogen, for example, I'm trying to make 1 mole of hydrogen gas from its constituent elements in its standard states conditions. By its constituent elements is hydrogen, and in standard states conditions, it exists as H2. So there is actually no change here whatsoever from hydrogen gas to hydrogen gas. So for any element, it's always 0, and you won't find that data in the data booklet. So this time I'll put the F first because that's the way we should really do it. That look like an F. Is 0 kilojoules per mole. Let's see if we can get that in. Yeah. Okay, brilliant. So always 0. So for any element, it's always 0. So always keep that in mind. Now, so I can actually ignore hydrogen over here because I know it's 0. But we'll input it into the arrow when we construct this cycle. Right. So let's start. Let's go with blue. I want to work out the formation enthalpies of this, and it always goes on the right-hand side of my arrow. I'm forming it, so it will go on the right-hand side. So I'm going to have an arrow going up. Now, that arrow represents the enthalpy of formation, and I might just have to write it underneath here, of ethene. Okay, That arrow also represents the enthalpy of formation of hydrogen gas. Now, we know this is 0 anyway, so sometimes you might not see it. I know that when this is sometimes taught, we sometimes see another arrow going up to hydrogen. I tend to keep it all on the same arrow, just so it looks a little bit more cleaner. Now, I need to know what are the constituent elements for carbon, ethene, which are carbon and hydrogen. So if we look at that, it's going to be made from carbon. Make sure the top equation is balanced. It is also balanced. Carbon solid. This is normally as graphite, in the form of graphite, and hydrogen gas. Now, what I do need is to make sure that this line is balanced. So the blue line that we've got here for the enthalpy of formation of ethene and the enthalpy formation of hydrogen is balanced on either side of that arrow, or that energy change, that enthalpy change. So I have 2 carbons at the top. I'm going to have 2 carbons down below here, and I've got 6 hydrogens at the top, and therefore we'll need 6 hydrogens at the bottom. And I do exactly the same thing with ethane on the other side, and the arrow will go up again. Okay, now the arrow has gone up because it's the formation of ethane. I need 2 carbons and 6 hydrogens, and I've already got that balanced below. On either side of this arrow, it is balanced in terms of elements, and that's really quite important. I'm going to call this the enthalpy of formation of ethane, and again, I'm going to keep state symbols in there. Now this time, you notice that I haven't called it delta H1, although I could write that there, and I could say delta H2 over this side. But what I'm actually going to use, I'm going to use these descriptors to represent delta HR at the top. So how do I go about doing this? Well, like I said before, put a dot where you want to start, dot where you want to end. So basically either side of this arrow, top arrow. I'm going to go down, across, and up. I'm going against this arrow here. So all of this, the sum of those 2 enthalpy changes is going to be negative, and I'm going with the arrow on this side, and that means that it's going to be plus. So the enthalpy of reaction, so I can put delta RH if I want to. It's not very consistent, but you can use delta HR like that, as I have with the previous part of this video, or you could use delta RH, but like I said in previous videos, this is a more common way of writing it now. Enthalpy of reaction for the reduction of ethene, gives us this following equation, if you like. So I always tend to put the positive first. So in fact, I will do that in red. So it's the enthalpy of formation, okay, of ethane minus, this is where I'll put minus in green, just open brackets. I'm going to just close brackets over here. Hopefully I have enough space. The enthalpy of formation of ethene plus the enthalpy of formation of hydrogen gas. Plenty of space. Right, okay, so everything within this bracket is going to be times by -1, that green minus, because we are going in the opposite direction shown by that in the Hess cycle. So this is, again, another description of the enthalpy of reaction for this reaction here. Remember, you can use delta HR if you wish to. Okay, right. So that's a quick explanation of how we have used formations. Now, in some texts, you might even just see, rather than the elements carbon and hydrogen, is actually you just have a box. So I'll do a little diagram here. So if we go from A to B, they sometimes just show a little box and they write elements in there. Now I've known this for OCR, and they just show that the arrows are going up. But it is still quite important that you understand why they're going up. What is in this box? It's quite important, and those are the elements. And the only way you know that is if you know the definition for the formation. So I'm going to leave formation there. In the next video, we will be looking at calculations. So definitely worth popping onto that video as well. Let's move on to combustions. In combustion, we're going to use the exact same reaction as above. So the reduction of ethene. Oh, there we go. Right, C2H6 gas, that's ethane. Still going to call it delta HR. In fact, this time I'll go delta RH. Still the same thing, like I said. But this time we're going to look for combustion. So what I'm going to be looking at here is we're going to be looking to combust ethene, the products, hydrogen, the products, and ethane. So what I'm going to do just quickly, just so that makes a little bit more sense maybe, I'm just going to label 1, 2, and 3. So if I go over to the right and I just look at 1, the combustion of ethene, complete combustion, we assume complete combustion, get carbon dioxide gas and H2O liquid. Right, so we need to make sure the equation's balanced. I need 2 carbons, I need 4 hydrogens. That gives me a total of 6 oxygens. Okay. I'm going to do equation 2, which is hydrogen, complete combustion, oxygen, gives me water. Whether it was complete or incomplete, you still get water. And I need half O2. And then the final one is 3. Ethane plus O2 gas, complete combustion, carbon dioxide gas, and H2O liquid. Right, and again, we need to balance it. 2, and I need 3 oxygens, sorry, 6 hydrogens, so 3 in front of there, so I need 3 oxygens, plus the 4 over here, so 7. So we need 7 over 2, or 3.5. I could have put here as well. Now I'm going to use these 3 equations to construct my Hess cycle. So this is the combustion of ethene. You can see that the arrow is going down. In fact, I'm going to stick to red. Just going to get rid of these lines underneath. Oops. Let's put that hydrogen back in. There we go. We have an arrow going down. Put that 2 back in. This arrow, again, like I said before, I tend to only put single arrows in, but you could put 2 arrows. You could put another arrow in for hydrogen to represent 2. But this arrow here that I've just drawn in represents equation 1, the enthalpy of equation 1 and 2. So it actually represents the enthalpy of combustion of C2H4 gas plus the enthalpy of combustion of hydrogen gas. Okay, that's what this arrow represents, and that produces carbon dioxide gas plus water liquid. Okay, now what we also need to do is, as always, balance. Now I've already balanced it over to the right, so I'm going to use that. I need 2 carbons, but this time I need to look at the whole thing. I need 6 hydrogens. That gives me 7.5 O2. So what I'm going to do, just like we did with the HCl, I'm going to put 7.5 oxygen gas on the arrow. Okay, and that makes sure that make sure that the equation is balanced, and I'm accounting for these oxygens here. Again, like I said, sometimes they don't show that in the textbooks even, but it's a good idea to know where they have appeared from. Get another red arrow, and this time, realize there's no 2 there, let's put that 2 in. Going down, and this arrow here represents 3 only. So that represents the enthalpy of combustion of ethane. That's gas. And again, I need to balance it. In terms of carbons and hydrogens, it's already balanced, but I need that plus 7.5 O2 gas. And you can see that I've included state symbols in both cases of those oxygens and throughout the rest of my Hess cycle. Now, how does this go towards, I'm just going to move this up a little bit. Move this up. Right, now how can I get the descriptor for my delta HR? How can I calculate delta HR if I had these values on the left and right? Well, again, I just need to, I'll get my green pen, put a dot where I want to start, dot where I want to finish. I'll go down, across, and up. But this time you can see that the first arrow we're going with, so it's all of this plus, but this one I'm going against, so it's minus. So how does that translate to delta HR? So that means the enthalpy of reaction for the above reaction is equal to, I always put the positive on first and put big brackets, I won't put the green in this time. You don't need brackets really, but I'll put that in just for consistency, similar to what we did before. Plus the enthalpy of combustion. So there's the enthalpy of combustion of ethene plus the enthalpy of combustion of hydrogen gas. Close those brackets, it makes no difference really. But again, like I said, doing it for consistency as we did above. Minus the enthalpy of combustion of ethane. Right, and that, as long as you have the values for each of these, which you can get from a data booklet, means you can calculate the enthalpy of reaction for the reduction of ethene via combustion, or, as we've mentioned, you can calculate the same enthalpy. You calculate the same enthalpy using formations. So basically, this one here, let's use this colourful pen. This enthalpy is exactly the same as this enthalpy, but we have gone through completely different directions. This one's using enthalpy of combustion, and the above was using enthalpy of formation. So it just kind of reinstates the Hess's law, kind of makes it more concrete that the enthalpy of reaction is completely independent of the route taken, and we've taken 2 completely separate routes, but we should still arrive to the same answer. Now that concludes this video. I hope it's been useful. If it's obviously been useful, please like the video and subscribe to see more videos. Even use the comments section to tell us what other videos you might want to see, and we'll try and create those for you. But thanks for watching, and we'll see you next time.